So in the first condition where we see as H11 and C11 for whole basis system, we'll refer to only this column for easy understanding. So this kind of combination can be used to define loose running clearance fits. So this is used for commercial tolerances or allowance for external members. That is, there's not going to be any interaction between the components together. It's just as a loose fit component between those two shaft and hole. So then you can go for this referencing. Next, for this, it's called as a free running fit. So this is used where accuracy is essential, but it's going to be applied for large temperature variations or high running speeds, or where heavy journal pressures are exerted. So in those conditions, you go for this free running fit. In this condition, that is a closed running fit. This is required for running on very accurate machines wherein you perform important tasks, and for accurate location of the components that is going to be used at moderate speeds or moderate journal pressures. Next, you have your sliding fit. You can see the clearance keeps on reducing, and in this sliding fit, it is not intended to run freely but to move or turn freely and locate accurately. In this condition, you use this. Whereas in the least part of this clearance, you have your location clearance. It's used to provide the snug fitting of the stationary parts. That is, it can be assembled or disassembled, but it has to be fitted by an external component that is using a snug fitting procedure. So next, you have your transition fit. So it again is going to denote in this zone. It either goes as a location transition in the clearance zone or the location transition in the interference zone. So that is, it's used for an accurate location, a compromise between the clearance and interference. Likewise, the same in this denotion where a greater interference is permissible for this denote. You can cross-refer this along this diagram to have a clear understanding like how it's going to be positioned. So next, in this interference fit, it means that in this condition, transition fit for basic sizes for 0 through 3 mm, you go for this 6 nomenclature, wherein the location interference fit is used for parts that requires rigidity and alignment with prime accuracy of location, but without any external bore pressure requirements. Wherein you still go for higher interference, wherein the objects, the steel object parts or shrink fits are used for the different sections. So this is what I was speaking about earlier, and going for a tighter tolerance, more interferences, that is the force fit. So it means that you either heat it out or shrink it or exert heavy stress, that is you hammer that element into the component. So that means that you have to have heavy pressing forces that are required to do it. So in these conditions, it means that though they are two different components, after fitting these, going to behave like a individual single component. So this is how you select upon the different fits that are required to you based on your application. So now let's look into the various tolerance grades that you have to determine. So till now what we've seen is various allowances, tolerances, and based on that, what is the different sizes that are going to use. Now we have to determine like what is the tolerance that I can allow for a given manufacturing process. So this is where your IT grade will come into. So this is defined in ISO 286, wherein 20 different grades of tolerances have been defined. So these grades determine what tolerances are allowed or can be specified for a given process. So it means the capability of a process. So based on that, the tolerance can be defined. So the first band, that is IT0 to IT6, it's a very tighter tolerance zone. It is used predominantly for the production of gauges and measuring instruments, because you are measuring the variation of a component, so you have to keep your tolerances as tight as possible, as close to your theoretical limits. So this is where the tolerance zone comes in, that is from 0 to 6 grade. Then you have an intermediate grade, 5 to 12. This is typically used for almost all the engineering processes, where you define a tighter precision as well as the tighter nominal grades of tolerance. Then a subcategory to it, wherein you have grades 11 to 16, it's used for production of semi-products, that is, they are still yet to be machined or manufactured to attain the final process. So it's a part of the sub-assemblies. Then you can go for this object. Then again, the higher side, that is grade 16 to 18, wherein the controlling of the tolerances is difficult. That is typically for civil structures and so on. And another broader specification, that is IT 11 to 18, that can be used for specification of limit deviations of non-tolerated dimensions. That is, the tolerances are not specified. In those cases, again, you can use these grades. So bringing all this process and categorizing them to the grade, you can see the variation. That is, the typical, the 2 to 0 to 6, okay, these components, you can see the processes that are going to be used here are processes that can result in high tolerances. So this is a lapping operation, honing operation, super finishing operation, cylindrical grinding, diamond turning, plane grinding, and then a part of a broaching, reaming operations can satisfy to the tighter tolerances. That is, accuracies going to micron levels. Wherein the next band, where we have is the 5 to 12, is a broader tolerance zone. There again you have your this process, that grinding process, reaming process, boring. Then you have your sawing process, that you can see a wide varying, because based on the different type of cutter, the boring and turning process, based on the different types of cutter, based on different cutting speeds, and hence you can control what's the tolerance that you have. So you have your sawing, milling, planing, shaping processes, that goes until like 15, 16 here, that has a slightly relaxed tolerance, because with this process you can't control the tolerances very closely. Next, on the higher side, you have the processes, that is extruding, cold rolling or drawing process, drilling, dry casting, forging, sand casting, hot rolling. These all falls under the higher category. That means that the typical differences goes in the order of mm. So how to determine it? So just have a quick go through of it. How these tolerance grades are calculated based on the grade is that, let us see what is the limit that is allowed. So this is the formula that is used to calculate it. The tolerance grade 1, 2, 3, whatever it is equal to 10 raised to 0.2 times of IT grade. Here is where you plug in your numerical grade, and then times 0.45 times of cubic root of your diameter, nominal diameter, plus 0.001 times of your diameter. So here the T is your tolerance in micrometers. Next is your D, that denotes your geometric dimension in millimeters, and then IT grade. So based on this table is, it can throw you a little light of what is the allowed tolerances. So if you could recollect the tolerance grade 2 to 6, where highly critical processes wherein you can give a tighter tolerances. So if you go by the basic side definition, that is controlling the D, you can say plugging onto the different tolerance values here, you can get the what is the maximum tolerance within which this object can be controlled. Suppose if you are operating with a smaller object, say with a 3 centimeter 30 mm size of thing, then these processes, the first 2 grade process, can control within 1.5 micrometer. So as we go on to higher tolerances for the same basic size, you can see the tolerances increases. So here until IT 11 you have like 110 micrometer, then going on further you define in terms of millimeter. That means that, for example, a 30 millimeter component going for a IT grade of 18 can produce a dimension variation of 3.3 mm. So this means that for this component, that is for 18, generally means that for these categories you cannot go for there's a control of what is the basic dimension that you can use for. That is for IT grades 1 to 5, that is where you have a tighter controls of tolerance. You typically go for only 500 mm, that is just 50 centimeters. So typically within this is what you control it. You have to look into only this zone. This is just for representative purpose. That is, there is no point of going for a tolerance of, say, with this process of 135, 96 micrometer tolerance for this huge dimension. So it typically does not make sense, because if you want to reduce this object, then you have to use a combination of different processes. You do not directly go for this tighter a specialized process. Rather you go for a process that calls for a lower tolerance and then gradually reduce the size. So this is how you have to determine between the various components. Likewise, in the higher zone, these are not used for basic sizes that is less than or equal to 1. Again, it makes sense, like for an object that varies between 80 and 30 mm, then the tolerance is going to be 3 mm. So it's typically used for a process that requires for a very high tolerance range. So let us go back to this previous slide to see typically how the object is manufactured. Is they are initially the tolerance is controlled in the first level by the first manufacturing, wherein you either the forge component, for example, if you go for a piston rod, okay, so you go for forging, wherein you initially control the tolerances, that is from a band 13 to 16 is where you have 13 to 16 you can see it lies to like in maximum of 30 mm, minimum 3 mm. So in this zone you specify the allowed condition for that operation. Next you go on to the next operation, then that is you go for a planning or shaping operation, then you machine it particularly, then you bring down the tolerance, then you go on to the next step, that is you control finer tolerances here. Then in order to measure this completely machined product, then you go for a gauge that are subjected to this machining process so that it can control you measure the variances that are very small tolerances of 1 micrometer or so. Your original object might be in the order of 5 microns. So this will constitute your at least a dimension that you can measure. So this is typically how your IT tolerance grades are defined in your standards, and you always have to have in mind. So this is your strong engineering practice that's going to go when you design a component. When you design a component, you also define like what is the process that needs to be followed to do that, and based on the different processes you have to draw your draft your drawings and specify the tolerance according to those processes. So this defines a very good engineer that has a good grasp of this condition. So next we'll look into the various symbols and modifiers that are going to be used in this GD&T terminologies. So this is the visual method of communication to the manufacturer as well as the inspector to indicate what is the limit dimensions, what are the methodologies that needs to be followed to ensure that the tolerancing is attained to. So first what we have is the different types of categories of tolerance. That is what is listed here. So these categories deal with the tolerance of the form, tolerance of the location, the orientation, the profile or the runout. So based on that we have the various geometric characteristics that are going to be controlled, and we have this symbolic representations of those characteristics. So each and every characteristics has specific prerequisites, that is whether datum reference is required or not, and then how it can be applied to the various feature, size, surface or the feature of size dimension. So whether this form can be applicated or not. So likewise, so this is how you must look into the various applications of these symbols. Next we have the modifiers. It means to say that it overrides the condition of the material. It will say what is the allowed material condition. So here the various parameters that we have here is the regardless of feature size RFS that doesn't have any symbol. Then we have the maximum material condition, least material condition, then the projected tolerance zone, and then unequal tolerance zone, tangent place. So it means that these modifiers go along with the symbols to convey the end objective to the manufacturer as well as the inspector. So we have to be very careful of what to use, and if suppose we are using one of this parameter, then the prerequisite as well as the essential conditions need to be satisfied, and only then it can be applied. So let us look into one by one now. So going forward, this straightness is the part of the form tolerancing, that is you are applying the tolerances to the form of the object. So this is the symbol for it, it's a straight line. So the definition goes like this: an element of a surface or axis is going to be straight line, and hence one of the surface elements is going to be constrained to lie within two parallel surface planes separated by the tolerance. It means that the form of that surface has to be constrained between two planes so that it does not exist. So any line across that surface in that view will be within those two parallel lines. So only then that part is going to be accepted and cleared for. So this is what straightness means. So let us look by this example. So here this is what we mentioned as a drawing. So this is a circular shaft, and In this view you can see that the cross section is going to be plane and the dimension is controlled with this tolerance specification of straightness, and it's applied to this symbol, that diameter surface symbol is within 0.01. So what it means is that on this surface you draw two parallel lines up and below with this tolerance, because see, your tolerance is going to be 2 plus or minus 0.02. So it means that 1.98 and 2.01 on the exterior. The maximum allowed is the controlled by this dimension, whereas the overall dimension is allowed by this point. So you can see that there's a slight variation between this. So the center line tolerance is what is going to control by the straight line. So within this zone of 0.01 of tolerance within this straight line, the material can lie so as to ensure that the overall tolerance is also not exceeded. So the outer boundary is controlled by this. So you can see that the external is 2 plus or minus 0.2, and over and above you have this tolerance of 0.01, and hence the overall tolerance is going to be, that is the stack up tolerance is going to be 2.03 mm, wherein at this exterior point, okay, so from this point to this point, that is the actual size element, there you are getting controlled by 1.98 only within this. But having applicated this tolerance width of 0.01, you will get that additional 0.01 mm that is getting added to this overall dimension. So this is how the form of this is going to be controlled. So this is how you can see the symbols is going to add on. The tolerance zone will control the shape, the form of this object. So you can slightly go through this command again. This tolerance is going to be the overall size tolerance that is permitted, that is the straight line that is drawn to here. Okay, so this is the allowed variation of that object, but considering the two datum planes wherein the straightness can be the datum reference plane to measure the straightness of this element. So for that the total dimension can vary. For this point the tolerance is acted upon, and hence it is 2.02 mm. So next, moving forward, flatness. It is an extension of the straight line. It's also a part of this form. It controls the form of the surface. So this is the symbol for flatness, and here it's a two-dimensional tolerance zone defined by two parallel planes. Earlier we were seeing as lines. So these are two parallel planes within which the entire surface must lie. So all the surface elements has to be constrained to be lie within those two parallel planes only, separated by the tolerance. So going by the same example here, if we specify this tolerance of flatness here with 0.005 to this overall dimension of 1.00 plus 0.01 mm, it means that you construct two-dimensional plane here. You can see here this element. In this view you can see this is going to be a base tolerance reference zone, and over and above you have this tolerance zone specification of parallel planes 0.01. So it means with this reference plane, this boundary of 0.05 is the maximum allowed flatness plane within which the object must lie. Likewise, on the lower side we have the other plane that you have drawn here. So this is your allowed flatness zone. So only this is your flatness zone. So you can't go below here also. So your base object is 1 mm here. Over and above you have your size tolerance as 0.01 mm. So this is your max boundary, and within this max boundary what can be the form tolerance is what is controlled by your flatness here. So this lies within it. It can never exceed it. The same can be seen in this form also. So this base lines, these two parallel lines is what the maximum allowed variation of this form. And this external height, this topmost, and so this is your maximum material height, that is going to be controlled by your size tolerance. So this is how your base tolerance and your GD&T tolerance symbol is going to play upon. So moving forward, the next form tolerance is your circularity. This is your third form tolerance element and it's represented by a circle. So here this circularity is a condition on a surface of revolution, that is a cylinder or a cone or a sphere, where all the points on the surface that is intersected by any plane perpendicular to a common axis of the cylinder or cone are passing through a common center of the sphere. In these cases, both the plane that is perpendicular to a common axis for a cylinder or cone or through a common center of a sphere are equidistant from the axis of the center. So for this circularity, all the points on the cylinder surface are constrained to lie within those two circles only. So this is going to be a 2D surface form tolerance. So here let us look with this example. So this is the meaning, that is size tolerance is 1 plus or minus 0.1, wherein the form tolerancing is a circularity with 0.002. It means that the overall size variation is going to be minimum 1.001, wherein the maximum size is 1.01, within which the external, these two circles, right, this surface and this surface must have only 0.02 tolerance that is allowed by your circularity element. So this is how you control your circularity. So next form of form tolerancing, we have the cylindricity. So the cylindricity is represented by this, so that in circularity you have two tangential elements. So a condition on a surface of revolution, that is your cylinder, cone or sphere, in which all the points of the surface are going to be equidistant from a common axis. So that is your cylindricity. So this is the extension to your circularity function. Okay, so it extends from 2D to a 3D based form control, which controls the roundness, that is the circularity, as well as it also controls the straightness and taper of your 3D form. So to better explain this, we have a figure here. So the same shaft of base dimension 2 with a unified tolerance of 0.02 on the plus side has a cylindricity of 0.01. It means that this on the overall on both, as you can see, this is controlled in this view as well as in this view, that is in 3D view, because here you have the two dimensions, here you have the third dimension, the two different planes. So with this, all the three planes are covered, which and by which the external boundary is limited by the form of a tolerance zone of 0.01. So this is your cylindricity that applies onto here. So these are the four forms of form tolerancing. So let us go back to this definition once more. So you can see now we have seen straightness, flatness, circularity and cylindricity. Now these are all apply to this thing. So there is just a difference between here. These two are wrongly represented. Cylindricity is represented by this and position tolerance by the other symbol. But these four are going to be your form tolerances. So these form tolerances are all can be applied to the feature surface, whereas feature of size dimension, that is a 1D surface, is the straightness alone, whereas all other, these two are 2D and this is 3D, and hence is not applied to the feature of the size dimension. Whereas for all these form tolerances, datum reference is not required. That is, it does not reference a reference datum. It can be directly applied to the form. So next what we are going to see is the locational tolerances, where we have position tolerance, concentricity and symmetricity. So we'll quickly look into one by one. So first is the true position, that is located by the symbol, by this kind of your center symbol. So what we are doing by this is that this is the zone, the true position is the zone within which the center axis or center plane of the feature of size is permitted to vary from its true, that is your theoretically exact position. So this is a position tolerance that generates a tolerance zone that confines your center axis or the center plane or the axis of feature. So it is also capable of confining a surface or surfaces within or outside a boundary known as your virtual condition. That means that in this figure you can see this is a rectangular plate that has true holes, a larger hole in here, whereas there are other peripheral holes that are drilled here. So now we can see there is some a box that are referenced as we've seen in the GD&T. This we'll look into this is called feature control frame that we'll look into later. But you can see now this cylindricity is applied to this holes to ensure that the position is controlled by it. So as you can see, it also refers to the datum planes here, and also it defines a material condition here. So what it means is that this true position is applied to this center. This center is allowed to vary only for 0.02 mm of this dimension. This is your true position. So based on this, it can be constrained only this variation. So this is your tolerance zone. Whereas this external whole dimension is controlled by a upper side positive deviation of 0.1 here and here. So this is what controls your position variance. So in essence, this center line that is drawn here in this view, it can vary only within a zone of 0.02 on either side. So this true position is applied to the center or the axis or center plane of a feature of size. So this is how you are applicating the tolerance to the location. So next we have concentricity. This is also a part of your location tolerancing that is represented by two concentric circles. So what it means is, it is a cyclical tolerance zone whose axis, this axis coincides with the datum axis, and within which all the cross-sectional axis or the feature being controlled must lie. So it means that this is going to be geometric control of the median points of all diametrically opposite elements of a figure of revolution. So it has to be measured by a instrument that goes throughout this cyclical zone to measure all the points that is referred and to the median point of all the diametrically opposite elements. So this is normally a very expensive and time consuming process to measure, and hence due care to be taken, and only those critical dimensions have to be toleranced by this concentricity. So here you can see in this example, we have a shaft with two different dias. We have a larger dia here and a smaller dia here, and for the smaller diameter shaft of 1 mm plus 0.03, concentricity has been applied with a variation of 0.2 with reference to the datum surface A. So it means that a center axis drawn through this plane can have a diameter tolerance zone of only 0.2, that is this exterior zone, within which all the median points derived from this surface. This is a revolutionary surface. It's not a 1D surface but a 2D surface on this plane. So all these median points along this entire plane should lie within this 0.02 diameter of tolerance regardless of its size. So this is controlled by your datum axis. So this is the datum axis. So this is your surface here within which the axis of actual mating envelope is contained. So this is how you contain the cyclical tolerance of a circular element. So next location tolerance is where we have a symmetry behavior. So this is denoted by these three lines. So symmetry is the condition where the median points of all opposed or correspondingly located elements of two or more feature surfaces are congruent with the axis or center plane. So it is similar to the concentricity in the point that it is again referring to the median points of reference, but it refers to two or more feature surfaces that are congruent with the axis or center plane of the datum feature. So this again calls for a datum feature here, wherein we have two surfaces here, and this location control is applied to these two surfaces and mentioning that these two have to be symmetrical along with this datum surface of A. So it means that for these two surfaces along this datum plane A, so for this datum surface what is the center plane, and for this center plane this is going to be the tolerance zone of width, and hence these 2 points have to lie within this variation zone so that the symmetricity of this surface and this surface is maintained with this surface. So this is the symmetry location tolerancing. So next is the orientation tolerance. So going quickly back to the overall chart, in this orientation we have three different types of geometric characteristics, that is we have a perpendicularity, a parallelism and an angularity. So these three controls the orientation of the feature surface and as well as the feature of size dimension. So earlier in this location tolerance, it applies only to the feature of size dimension and not to the feature surface. So likewise in this orientation, it applies for both the feature surface and feature of size dimension. And for this orientation tolerance, we definitely refer a datum requirement. So let us go back to our slide.